In our last lecture, we looked at how can we classify different members based on their force transfer mechanism. So we saw that we could expect tension members, compression members, beam columns in a typical structure. Now we have already looked at uh, an introduction to what tension members are. So, just to brush up and give it a good start. So tension members are structural elements that are subject to direct axial forces which tend to elongate the members. Simple. Now, we also looked at the fact that these members carry uniform stresses, meaning that if I cut a section along a tension member, the entire section will have the same tensile stress, which is equal to the tensile force upon cross-section area. Now, theoretically, these members are 100% efficient. Why? It's because the entire section is actively participating in resisting loads, which is unlike a beam section, wherein the stresses at the extreme fibers are high, but along the depth of uh, the section varies and it is zero at the neutral axis. So theoretically, these are 100% efficient, but practically, no, because in order to connect these members, if we happen to use bolts, then we are putting in bolt holes, because of which the gross area reduces to net area. There's a reduction in the area, which we look at, and how to calculate this area, we look at that as well. So that's why theoretically they are 100% efficient. Now, since the entire section is stressed, we can sort of stress it up to the yield stress, and also we can go on to stress it further to the ultimate stress. And one advantage that we have in tension members over compression members is that tension members do not tend to buckle. Like we saw in compression members, that if it's a slender compression member, it's going to buckle. That's not the case with tension members. So that's an add-on here. Now we also looked at the common examples of tension members. Uh, the most common being the chords members in trusses, the diagonal bracing. So whenever the building is designed for lateral loads, and we happen to use a bracing system. In that case, the members of the bracing system are tension and compression members. Then the cables and suspended roof system, and then the suspension bridge main cables and suspenders. So these are the common examples of tension members. We also looked at the common or the typical cross sections which are used as tension members. Now, this particular slide corresponds to the numerical that we solved, and I believe this has already been explained. Now, I've put this in a slide so that we can solve such type of questions. In that, I've just rearranged what we learned there. There, we had to find out what is the value of P, or what is the axial load. And here in this, it's just that elongation. So if we know the value of axial load, then how to find out the elongation? So you can just take a look at it later. Now, this is the most important uh, part of learning tension members. See, if we know how a member is going to fail, or if we know various ways in which a particular member can fail, then we can design that member such that none of the failures occur. Okay, we talked about limit states. Now, these are the possible limit states for a tension member. These are called, first, cross section yielding, second, net section rupture, and third, block shear failure. So, if a member is under tension, you can expect it to fail by either one of these three. Okay. Now, when we say design a tension member, what do we exactly mean? What we mean is that we should make sure that it should not fail by either of these. So how do we do that? So first we sort of start with uh, the mechanism number one, that is cross section yielding. We find out the force at which cross section yielding might occur. Okay, let us call it T1. Then we consider net section rupture, and we find out the force at which this might occur. Then we calculate T2. And finally, we consider block shear failure, and we find out the force at which that will occur. Let us call it T3. So now we have three forces, T1, T2, and T3. Now, can you sort of guess as to which of these would be our design stress, design force? Meaning that which of these is the minimum force that the member can take? Is it the maximum of T1, T2, T3, or is it the minimum of T1, T2, T3? So let us say the force at which this fails is T1, the force at which it fails by net section rupture is T2, and the force at which the block shear failure occurs is T3. See, we'll get into what these are, what these terms mean. We'll get into it later, but just to give you a glimpse of what we're trying to do here. So if this is the force at which this occurs is T1, this is T2, and this is T3. Now we have three value of forces. So what is our design force, or what is the maximum force that this member can take? Is it the maximum of these three or minimum of these three?
Minimum.
Any more thoughts? Okay. So our design force is the minimum of these three. Why? Because at the minimum value, one of the failures would occur, and then we really don't care if the other failures occur or not. So our member has failed. So our objective here is that our member should not fail for any of these three. So if either T1 or T2 or T3 reaches, then the member has failed. And therefore, our design tensile force is the minimum of these three. So what we are principally going to do is, for any given section, we are going to find out T1, we are going to find out T2, we are going to find out T3. And our design tensile force is the minimum of T1, T2, and T3. Any questions here? Just in case you're not understanding, just come ahead and ask questions. If you want me to explain it again, tell me
Yeah,
that way.
can you please explain the last part again?
Okay. So we are talking about various ways in which a particular member can fail. Now, the member is failed if either one of the phenomenon occur. Okay, so let us say that we have three ways in which a tension member can fail. So even if one of the phenomenon occurs, the tension member has failed. Okay, so what do is we find out the force at which it fails by gross section yielding. Let us call it T1. We calculate the force at which it fails by net section rupture. Let us call it T2. And then we calculate the force at which it fails by block shear failure. Let us call it T3. Now we have three values of forces. Our question is, what is the maximum force that I can apply on this section? Okay, so the answer to that question is that force, or the design tensile force, is minimum of T1, T2, T3. Why minimum and why not maximum? Because at a minimum value of T1, T2, T3, one of these failures would occur and my member has failed, right? So the maximum force that we can apply on a member is the minimum force that can cause any of these failures. Okay, I just repeat it. The maximum force that we can apply on this member is the minimum force at which one of the failure occurs.
Bhargav, could you give an example? Because it's a little complex to understand. Like,
Okay.
in the sense.
Okay. So let us take an example. Uh, if I, there are three ways in which this can fail. I know that. So if let us say that T1 is equal to 100 kilonewton. If T2 is equal to say 90 kilonewton, and let us say T3 is equal to 110 kilonewton for a particular member. Now I have to find what is the maximum force that I can apply on this member. Okay. So the maximum force that I can apply on this member is the minimum of T1, T2, T3, which is 90 kilonewton. Now why maximum? So why minimum? Let us say that we start loading this member. Okay, so say this is a tension member that we are starting to load. So now the load is 10, we move on to 20, 30, it will start elongating, then we move on to 50, then we move on to 80, and then we move on to 90. The moment it is loaded to 90, this failure might occur. And the section has failed, or the other member has failed. And then these numbers are really not relevant because it is already failed by net section rupture. Okay, and therefore 90 is the maximum load that I can apply on this member, and therefore that is my design load.
Yeah, I think it's a very clear now. I think, yeah, thank you.
Okay, and that is a design load. So now let us look at what these terms mean. What does cross section yielding, net section rupture, and block failure mean? Okay, now the name itself says that it is gross section yielding, meaning that the entire section of that tension member is yielding. Now I just want you to get comfortable with terms like section and because whenever I say section, you should be able to imagine what a section is. So a member is a member and a section is a section, meaning that if say if this is an angle member, so this is an angle member elevation. If I draw a section, it is going to look like this. So when I say section, this is what you should imagine. So if it's a rectangular section, this is the elevation. If I cut a section, this is our section. So whenever I say section, this is what I mean. Okay, the same can be with I. So this is this is an I member. If I draw a section here, so this is my I section. Okay, so gross section yielding means that the entire section is going to yield. Now, without bolt holes, the tension members can resist loads up to the ultimate load without failure. Okay, this is what we have seen, that as you start loading the member, it will reach yield stress, but it will not fail because there are no holes. And therefore, when you load it further, it can even reach its ultimate stress. Okay, but the elongation, or we have seen that it can strain a lot, right? So the elongation is about 10 to 15% of the original length before rupture. So even though after yield stress, it has not failed, but the elongation is so much that the structure cannot be serviced anymore, or the structure becomes unserviceable, meaning that the deflections might be so large that you cannot use the structure anymore. Even though the section is not failed, the section is still intact, it has not fractured, but it has elongated so much that you cannot use it anymore. Therefore, instead of limiting our strength to Fu, we limit our strength to Fy. Okay, so just to look at our favorite stress strain diagram again. So I hope you already know that this is Fy here. What's wrong with this cursor? This is Fy here, and then this is Fu here, and this is Fy. So what I'm trying to say here is that even though the material fails at this point, okay, but when we are talking about using this material in a member, like a steel member, if we consider this as our failure criteria, what will happen is at this stress, the strain is so much that the member, which was something like this, now has elongated 10 to 15% more, because of which your structure might experience a lot of deflections, and because of that, it cannot be used anymore. So instead of using Fu, we limit ourselves to Fy, where the reflections are not much. It is still elastic. If you remove the load, it will go back to its original length. And therefore, we say that Fy is our failure stress. Okay. Therefore, the design strength is limited to the yield stress. Now, the question is, how do we calculate the force corresponding to this? The answer is very straightforward. Okay, now it's better. So we want to calculate what is the force. Now we have seen that stress is equal to force upon area. So if I want to calculate force, so force is equal to stress into area. But we have learned about partial safety factors. Okay, and whenever we are dealing with material strength, we divide it by a partial safety factor. So naturally, there will be a partial safety factor here, and that is how we get our first T. So first T is nothing but the stress. What stress are we talking about here? It is a yield stress. Okay, then stress times area. Now what is this area? This is the gross area or the total area of the cross section. So this area is denoted by AG. AG. So D stands for gross, A stands for area. And then just divide this by partial safety factor. The partial safety factor is given by gamma M0. So this is our formula to calculate our first tensile force, which is denoted by TDG. Okay, now these notations might seem to be confusing at first, but as we move forward, we'll get used to them and we'll understand what each of these means. Now, T stands for tensile force, D stands for design, and G stands for gross. Therefore, TDG. Therefore, this is the design strength corresponding to gross section yielding. So we get a simple formula. TDG is equal to AG Fy upon gamma M0. Okay, wherein AG is the gross area of the cross section, Fy is yield stress of the material, and gamma M0 is the partial safety factor for failure in tension by yielding. Now, if we go back, we see that the value of gamma M0 is 1.1. Okay, so perhaps I'll just add it here so that you won't have to go back to that slide. So the partial safety factor for failure in tension by yielding is 1.1. So this is the simplest formula that you will see in this entire course. TDG is equal to AG into Fy upon gamma M0. Now, I always suggest, and even that is the way that I remember various formulae, is that never just remember the formula. Just if you sort of have an idea of how we got there, then it's easier to recall it even if you don't remember it exactly. So this is how we broke up, and this is how we arrived at this formula. So if you sort of have this at the back of your mind, you will always be able to arrive at this, even if you don't exactly remember what it is. Okay, now here it's very easy, it's very straightforward, but you will see that as we go on, the length of these formulas are going to increase. So just for that, a heads up for that. Now the next type of failure, before that, any questions up to here?
Marco, could you repeat that last part again?
What last part?
The one where you were explaining the equation. I was a
Do you
bit
want me?
lost in.
Do you want
If
me
you
to
could just do a
repeat this?
quick run through. Yeah, if you could just do a quick run through of it, because I think I understood it, but I'm not fully sure.
Okay, so we are trying to find out the force at which gross section yielding occurs, meaning that we are trying to find out the force at which the entire section yields. Okay, meaning that the stress in the entire section is Fy. Okay, so we know that stress is equal to force upon area. We are trying to find out what the force is. So we will multiply stress into area. So this T is equal to stress into area. But we have seen that for finding out any design strength, we divide it by a partial safety factor. So force into area divided by partial safety factor. What is the force? Force is, what is the stress? Stress is Fy. What is the area? It's the gross area because we are talking about gross section yielding, and the partial safety factor is gamma M0. Therefore, our TDG is equal to AgFy upon gamma M0. Area into stress divided by partial safety factor. Is that clear?
Kind of. So the T does not. So the T stands for. That was
T
my main
stands for
confusion of the T.
T stands for tensile force. Now we are
Oh,
not using
okay.
capital F here is because we have tensile force, we have compressive force, we have shear, we have bending. So there are different notations for each of these. Okay, so normally an action load is denoted by P. Okay, but here in the ICE code, the tensile force is denoted by capital T. It's easier to remember that way. The compressive force is denoted by capital T. So T stands for tension, or T stands for tensile force. And DG stands for, so this is a design, D stands for design, G stands for cross section yielding. So this is a design tensile force for cross section yielding.
Oh, so this is basically an application of the same force area, stress, and partial safety
Yes,
factor formula.
yes, something that you've learned in junior KG. Force is equal to stress is equal to force
Yeah.
upon area.
Now
Okay,
that I connected
nothing
the
new
two,
here.
now I understood the whole thing. This is just the tensile forces a bit.
Yes, so nothing new. It's just we are rearranging thing and we just trying to find out what we need. Okay, is that clearer now? Can we move ahead? See, it's
Yes,
really
thank
important
you.
that you understand this because only then we'll be able to solve numericals and we'll find those easy if you understand this. Okay, so moving on. Next is net section rupture. Now, though the name of the mechanism itself suggests that we are talking about a net section, meaning that we are talking about whatever section of the member is left after we provide bolt holes in them. Now, let us try to understand what net section is. So if let us say that we are talking about a, a plate section. If I cut a section here, there is a plate. And then this is my cross section. This is AG. Now let us say that I am now connecting this to other members by using bolts. So what I've done is I've punched bolts here and then I'll punch bolt in the other member as well. Then I'll place these members over each other and I will use bolts to connect them. So now in that case, if I cut a cross section here, you will see something like this. Right? There's nothing in between. Therefore, this is the area that we have lost. The remaining area is called as the net area. So that's the difference between gross area and net area. I hope you understood this section.
Yeah, yeah.
You can imagine it, right? There's a bolt hole. I just take a section there. Perhaps you will see lines here, but there's going to be nothing in between. Oh, you will not even see those lines. So this is correct. This is how you will see it, and this is your net section. Okay.
So working on the idea that there's some math missing in the load transfer.
So see now, when we are talking about uh, when we are trying to find out the section strength, we always talk about missing sections and not missing mass. This has got nothing to do with mass. What is of importance to us is what is the area that we have. Okay, and based on that area, we'll get our stress. So here, to transfer the same amount of load, we have a larger area, so the stress is going to be smaller. Here, to transfer the same load, we have smaller area, which means the stress is going to be more, right? Okay, I don't want to complicate things a lot. So stress is equal to force upon area. If this is constant, so which means that stress is inversely proportional to area. T is constant. So gross area, if you have gross area, the area is large, the tensile stress is going to be less. If we have net area, the net area is smaller and therefore the stress is going to be larger. So everything is a function of area here and not of mass. Okay, and the objective of this was trying to understand what is net area. If you have understood that, we can move ahead. Are there any questions? I take it a no. So what is happening whenever we punch in bolt holes, the gross area is converted into net area, and there's a reduction in the cross section. Okay. Now, in general, even in our life, whenever there is a sudden change, it always leads to some kind of a stress. For example, let us say that you are looking in your phone and walking on the street, and suddenly there's a pothole, or suddenly there's a step. What happens is, your body sort of gets into stress. So whenever there's a sudden change, there's always a stress. Now, whenever there was a change wherein you wanted to shift from classrooms to this online thing, there was stress initially. Now when you're going to transfer from this online system to back to the classes, there's again going to be a stress because you're not used to it. So whenever there's a sudden change, there's always some kind of a stress. So even if you see here, uh, if you look at this particular section, now if we take a section that is far away from the bolt, the stress is going to be more or less uniform throughout. Okay, but if we look at the stress in and around the hole, you will see that there's a larger stress very close to the hole, and then as you go away from the hole, the stress reduces. To understand this, I'm sure that you might have crossed a bridge over a river, and if the water flow is always very turbulent along the piers of the bridge. If you look at a far off distance, the flow is uniform, but just adjoining the pier of the bridge, the water is very turbulent. Because of that pier, the pier is obstructing the flow of water, because of which there is turbulence. Similarly, here, the flow of stress is uniform here, but as you reach this point, there's suddenly a hole, and the flow of the stress is now disturbed. So, very near to this hole, the stress is going to be larger as compared to the average stress. Okay, now from the theory of elasticity, this maximum stress is about 2 to 3 times the average stress. Now, why are we talking about this? Because for the same tensile force, here the stress is uniform, but in and around the bolt hole, the stress is very high near the bolt holes, and the stress is lower as we move away from the bolt hole. We're just trying to understand what happens when we punch in a hole. So after we've punched a hole and we start loading it, this stress is going to be higher than the rest of the stress. So as we load it further, this stress will reach Fy before all the other sections. Okay, so as we load it, this section, the stress at this point would reach Fy first. What happens when you load it further? Now we know from the stress strain diagram that we have this plateau where the stress remains constant. Okay, so as we load it further, the stress here is not going to increase. So what will happen? Now the yield will spread in the outer areas. So initially, if we had only one point where the stress was Fy, when we load it further, the stress at the adjoining fibers is now going to reach Fy. So look at this figure. So initially, the stress was higher here. As we loaded it, the stress here reached Fy. When we loaded it further, meaning that when we increase the tensile force further, now this stress cannot increase because it has already reached its limit. Therefore, what will happen is now the other fibers which have lesser stress will now start to reach the yield stress. And we'll have a stress distribution something like this. When we load it further, the entire section would have yielded. Okay, but rest of the section, this particular section is still has a lot of capacity. It has not reached yield stress. This section has, because it has because it has a lesser net area. On loading it further, finally the stress in this entire section would reach Fu, and then it would rupture. And this phenomenon is called as net section rupture. let us just take how let us just take a look at how the experiment looks, and we'll discuss if you have any questions further. So this is an arrangement in which these are bolt holes, and we are applying load using a universal testing machine, and then we're going to see how it fails. As you might see, this has already started warping here. There's a lot of stress here. You can see these bolt holes. They are now visible, meaning that there's a lot of elongation there. If you could not final part. So you see, this is the net section rupture. The entire section is ruptured. So this is what we expect to happen in and around bolt holes. So now any questions here?
So when we look at the next net section rupture, we always look at the weakest section, right, in terms of
Yes,
area.
yes, perfect. Yes.
Like if I have multiple bolts, then I'll look at the place that's been punctured the most.
Yes, you are going in the right direction. So what he means to ask is that, say if this is a plate and I have number of bolts. For example, in this section, if I have 2 bolts, in this section I have 3 bolts. So this is our weakest area, and this is where we expect here we might expect the net section rupture to happen. So this is the next step. We always have to find out which is the most probable failure path, or which is the path along which the net area is minimum. So if you go along this path, the net area is minimum because here there are 3 bolt holes.
And this path cannot be diagonal to the force, right? It has to be perpendicular.
We
to the
will
direction of
look at
force.
that. We will look at that. So let us, okay, to help you understand this better, these are 2 different situations. Given that everything is the same, meaning that the tensile force is same, the section is same, this section is more likely to fail, or this section is likely to fail at a lower load because the net area is lesser here. The net area is greater here. Any more questions? Okay, then let us look at how we find out a formula for this. Now we have seen that stress is equal to force upon area. I'm denoting force again by T. This is our area. We want to find out what is the force. So the force is equal to stress into area. So it is equal to area into stress. And if we are talking about design force, then it is equal to area into stress upon partial safety factor. Okay. So when we are talking specifically about net section rupture, we will denote this by TDN. So T stands for tensile force, D stands for design, N stands for net section rupture. Now, which area should we consider here? Naturally, the net area, because we are talking about net area. Which stress should we consider here? Should we consider here Fu, or should we consider here Fy? Naturally, Fu, because we are talking about rupture. So this is An into Fu upon partial safety factor. Now, if we go back to this, the resistance governed by ultimate stress is gamma m1, which is equal to 1.25. So this value, this is gamma m1. Previous one was gamma m0. This is gamma m1. So this is partial safety factor for failure in tension at ultimate stress. Now, just so that you wouldn't have to go back and refer to this, I'll write it here itself. This is equal to 0. This is equal to 1.2. But there's one more term here, and that term is 0.9. The question is why 0.9? So if we look at the stress strain curve, yeah, so if we look at our stress strain curve, if we say that the failure stress is Fy, there is a lot of reserve strength in the material. There is still a lot of reserve strength in material, which is between Fy and Fu. Okay, but when we say that the failure is occurring at Fu, there's no further reserve strength in the material. We've already exhausted all the strength. So we just need some more cushion so that this is not actually reached. So this 0.9 is to account for the absence of any reserve strength beyond ultimate stress. So this is like a partial safety factor, but since we are talking about a very specific kind of failure, we cannot define a new partial safety factor for that. So to account for that, we use a factor of 0.9. By using 0.9, we are reducing the design strength by 10%. So that 10% gives us a cushion that there has to be this, since there is no reserve strength about this. Is it clear? And this silence is scary. This could mean that a
Bhargav,
majority of not understood anything. Yeah.
I had a doubt. Why are we taking Fu like the ultimate stress? Why can't we take Fy? Because like that is where the deformation of the material will start. So then if you are taking that in the cross section yielding, then why not Fy even here?
Because here, okay. So when we talk about the gross area, so let us say that this is a section that I've cut from a plate. So this is my gross area. And if we are talking about the stress at this area, Fy, now here you can expect this stress to be there along the entire length of the member.
Hmm.
Okay, listen to me carefully. So if this is your member in elevation, at this section, 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 everywhere you might expect the stress to be Fy. Why? Because this is a tension member. Everywhere the force is same, so everywhere the stress is going to be the same.
Yes.
Okay. But when we are talking about net section, so let us say that if this is where I put the bolt, so here I have net area, here I have gross area. Okay.
Yeah.
Here I'm going to have a higher stress. So let us say this is F1. Let us say this is F2. F1 is going to be greater than F2. As you load it, F1, so let us just look at numbers. I think it's easier to understand that way. These numbers are only indicative. They do not mean anything. So when we start loading it, say F1 is 200 and F2 is around 60. We load it further. F1 reaches 250. This has reached 80. So this has already reached yield stress.
Hmm.
Does it mean that all the sections along the member have yield stress? No.
Hmm.
The other sections have a stress of 80 only. Okay. When we load it further, then this might reach 300. This will reach 100. Still no problem here. When we load it further, this will reach 410, which is Fy, Fu, and this will reach somewhere around 170. Still no problem here, but there's a problem here. At this, only that section will rupture.
Okay.
So here, since every section has that kind of a stress, so the elongation is going to be much larger.
Hmm.
Okay, here we are talking only about this section and nothing else. So elsewhere, the stress is still lesser than, it might even be lesser than Fy. But here we have already reached Fu.
Yeah.
That is why we talk about rupture here, and that is why we talk about yielding here.
Okay.
That was a very good question, and I think that something that I should have explained in the first place, but because of your question, this explanation came out, and I hope everyone understood why do we talk about gross section yielding, and why we talk about rupture in the net section. Any more questions? Okay, perfect. So now let us see how to calculate AN. Fu you already know, gamma m1 you already know. Let us just see how to calculate AN. Okay, so just imagine that. So this is our tension member, this is our plate, and then let us say that this is our gusset plate. Might be a new term. So if you look at any connection where the member ends, you will always see that this member is connected to a plate that has this kind of a shape. So this plate is called as a gusset plate. We'll look at it towards the end of this chapter. So let us say that a tension member, which may be a plate section, is connected to a gusset plate. Now you see this dotted line here because this plate is below, or this gusset plate is below this plate section. So just imagine that there's this gusset plate and this member is placed above it. And that is the reason why you see a dotted line here. And then these are connected by this set of bolting, which is called as chain bolting. The number of bolts are same along all the rows of the bolt, along all the columns of the bolt. And therefore, this is called as chain bolting. Now, in this case of chain bolting, let me take a screenshot. So for chain bolting, if this is the failure path at this particular section, the failure path at the second column is going to be the same. The failure path at the third column is going to be the same. Now, going back to the question that Shravan asked, can it be that it can also go diagonal? So can it happen that it will go here and then here and might fail like this? Can someone answer this question?
I don't think so. At least not with the video you showed us with this.
It won't happen
See,
because
forgot the name of that strip.
see, stresses, failure surfaces, everyone just like us are very lazy. Now, tell me, if it has an easier path, why would it go on a long cut? Let's go for a shortcut, right? So the failure path always takes the least or the easiest path. So this is the easiest path. If he goes diagonal, it will unnecessarily take a long cut, increase the travel so this distance is definitely larger than this distance. So it is not, the failure path is not likely to travel like this. It will always, in case of chain bolting, it will always travel like this. This is our net section in case of a plate section. Now, how to calculate the net section? Now, from the previous example that we saw, if this is a cross section and there's only one bolt hole, then this is a net section. Okay, so if this is the width of the section and this is the thickness of the section, the gross area is width times thickness. What happens here? Here we have a bolt hole. Let us say that the diameter of hole is dh, and then this remains the same. This is b. So net area is equal to, and this also remains the same, T. So net area is B minus diameter of hole into thickness. Now we are reducing this area. We are concerned about this area only. This area is not there. So we reduce this. This is B minus DH times of T. So this is a net area. What if we have multiple bolts? In that case, the formula would be B minus N times of DH times of T, where this N is the number of bolts along that path. If we take this example, here we have 1, 2, 3, 4. In that case, N would be 4. Okay, so net area is gross area minus hole diameter times thickness of plate. If we simplify it, we get B minus N times of DH times of thickness. Now the question is, what is DH? D stands for diameter, H stands for hole. So this is diameter of hole. So does the diameter of bolt, or let me put it this way, is the diameter of hole same as the diameter of bolt? Do you understand the difference? You're talking about diameter of hole, and then we are going to have a certain diameter of bolt. So will diameter of hole be equal to the diameter of bolt?
It will be slightly bigger, right?
Slightly bigger, right? That's simple logic. If you have the same diameter, yeah, how will it go through? Because it has to have a certain breathing space, right? There has to be a certain tolerance. If it's exact same, it's going to be difficult to put them in. So the diameter of the hole is slightly larger than the diameter of the bolt. The question is, how much larger? Okay, normally it is around 2 mm. The IS code gives us a table saying the diameter of hole or the clearance is based on what is the diameter of the bolt. If the diameter is between 12 to 14, then you might give 1 mm tolerance. Meaning that if it is between 12 to 14, this will be between 13 to 15. If it is 16 to 22, we'll have 2 mm. If it is 24, then we'll have 2 mm. If it is larger than 24, then we'll have 3 mm. Don't worry, you don't have to remember this. In general, if you use 2 mm in any numerical question, I'm okay with that. This is just to give you a feel of what should be the clearance for what a range of the diameter. Okay, so we can say 2 mm is a safe number. We can say 2 mm. So if the diameter of the bolt is 20, the diameter of the hole is going to be 22 mm. 2 mm tolerance. So just remember that here you are concerned about diameter of hole. You're not concerned about what is the diameter of bolt, because hole is something that you are making in that section. Okay, so this is diameter of hole. So B minus N times of DH into T. Simple. See, if you're not understanding this, tell me right now, because we are going to take a step ahead and look at a more uh, involved formulation of this. So if you do not understand this, right now is the time to stop me. Okay, I take it yes. So this is about chain bolting. Now, sometimes might happen that instead of a bolting like this, to increase the efficiency of the connection, you might have a bolting like this. Okay, so what happens now is that, so if say this is your section, this is a member, this is how the bolting is done. So in that case, now the failure path is not same, right? So the failure path can be this, or now the failure path can be this, or the failure path can be this. We cannot know for sure because we do not know which path gives us the smallest value of net area. We do not know. We'll have to find out. Such an arrangement of bolting is called as staggered volting. Such an arrangement is called as staggered bolting, where instead of providing the same number of bolts in every column, you stagger them, and doing so sort of increases the strength of that connection, or increases for lesser number of bolts you can carry the same amount of load. That is why staggering is preferred wherever possible. So when you have a staggered arrangement, there is no constant failure path. Here you knew that every column of bolts would have the same net area. Therefore, there was only a single failure path. But when you move to a staggered arrangement, now there is no single failure path. There are multiple possible failure paths. Okay? Before that, the distance between, for example, I'll go here. The distance between the center to center of bolt holes in the direction of the force is called as pitch. And the distance between the center of bolt holes perpendicular to the direction of force is called as gauge. It's given here, don't worry. So the distance, the center to center distance between adjacent bolt holes in the direction of force is called as pitch, denoted by small p. Okay, and the distance between the center to center of adjacent bolt holes perpendicular to the direction of tensile force is called as gauge. Okay, it is denoted by small g. And then there are other notation terms as well. For example, the distance between the center of the bolt and the nearest edge is called as edge distance. Okay, not so this is good to know, but we're not okay. This is called as edge distance. So this is pitch, this is gauge, this is edge distance. Now the question is how to calculate net area in this case. Now the failure path is something like this. So how do I calculate this length? How do I calculate this length, and so on? So geometrically, it's one step ahead of what we saw before. What the code does is the code sort of simplifies the calculation of net area by giving us a common term, and that term is p square upon 4g. The first thing is don't get scared looking at these formulas. These are very easy and they'll become so common that you'll remember them at the tip of your tongue. Okay, so initially what we add is b minus n times of dh times of t. What the code says is, in case there's a staggering arrangement, here there's this plus this, so this length is slightly larger as compared to this length. So if I say that 1, 2 and 3, so 1 plus 2 is going to be greater than 3. We know this from Pythagoras theorem. Okay, but it's practical difficult to calculate what is 1, what is 2, and then find the net area and so on. So the code gives a simplified formula. What the code says is you just add p square by 4g for every stagger that you see. Okay, you just add p square by 4g. So for example, if I am moving along the path A, I'll just clear this out. So if I'm moving along the path A, B, F, G, then let's just say I'm moving along this path. Along this path, I encounter 2 bolt holes. So my N is going to be 2. And along this path, I have one staggered arrangement with a pitch of P1 and with a gauge of G1. So what would be my final formula look like? It would be B minus 2 times of diameter of hole, and plus, for I have one staggered arrangement, so I would have P1 square by 4 G1, and I have to multiply this entire thing by thickness. Okay, now let us take another example. In another example, my failure path is A, B, F, C, and D. This is my failure path. I'm encountering 3 bolt holes here. So N is going to be 3. And I have 2 staggered arrangements. So my formula would look something like this. B minus 3 times of DH, because I have 3 bolt holes, plus this is first stagger, has P1 and G1. So P1 square upon 4G1. Is there one more stagger? Yes, here. That has P1 and G2. So plus P1 square upon 4 times of G2 into thickness. Okay. Now let us take another case wherein the failure path would look something like this: A, B, F, J, K. Along this path, I have 3 bolt holes and I have 2 staggered arrangements. So the formula would now look something like this: B minus 3 times of DH plus the first stagger has a pitch of P1, gauge of G1. So P1 square upon 4G1. The next stagger has a pitch of P2 and a gauge of G2. So the formula would be P2 square upon 4G2, and we multiply this entire thing by thickness of the plate, and this is how we get the net area. So the first step is just try to figure out what are the different failure paths, and in all of these paths we will find out the net area. Let us say that this is the net area for this path. Let's call this is AN1, this is AN2, this is AN3. Now tell me, what are we interested in? Are we interested in the smallest value of these AN, or are we interested in the largest value of these ANs?
Smallest value.
Why smallest? Because
Because
just like us, the failure path is lazy. It will take the shortest possible path. Which is the shortest possible path? The path that has a minimum value of AN will be the shortest possible path. And therefore, we find out all these ANs, and whatever gives us the minimum value is our AN.
Sorry, Bhargav, but just a clarification.
Yeah.
So this shortest part is also automatically the weakest part, right?
Yes. The shortest path is the weakest path, and you will expect net section rupture along that path. In case of chain bolting, there's only one path. In case of staggered bolting, there are multiple paths. Okay. So do we like go crazy and find all the paths? The answer is yes. We'll have to find all the paths, and then determine which path is the weakest, and that is the path along which we'll expect net section rupture. Easy? Nothing difficult. This is pure logic. Okay. So let us pause here for a moment. Give your brains a little break, and then we'll start with a numerical. We'll put all these concepts into numbers, and then just see how to calculate this, how to calculate net area for a chain bolting, and how to calculate a net area for staggered bolting. Okay, so it's 10:20. Let us meet back at 10:25, and we'll solve a quick example and conclude our lecture for today. In the meanwhile, if there are any questions, I'm here.
Hi, Bhargav. My net crashed when you mentioned something on the slide about the minimum. Could you just please repeat that?
Please write down. Determine the minimum net area. Determine the minimum net area determine the minimum net area of the plates shown in figures A and B. The plates shown in figures A and B with plate size of 260 by 10 mm with plate size of 260 by 10 mm and 20 mm diameter bolt and 20 mm bolts. After you're done writing, please draw the sketch. Determine the minimum net area of the plates shown in figures A and B. I'll draw B. I'll show you figure B later. With plate size of 260 by 10 mm and 20 mm diameter bolts. Okay. So now this is chain type of bolting. So how many failure paths are possible in this kind of an arrangement?
Three.
The answer is one.
One.
The same failure path can occur here or here or here. Okay. So we might have a failure path like this. So 1, 3, 4, 5, 6, and the same failure path can happen here or here. Okay. So Let us begin solving this. The first thing is that we've been given the diameter of bolts, but not of that holes. The diameter of bolt, this B is in suffix, okay? Or the diameter of bolts is equal to 20 mm. So the diameter of hole is equal to diameter of bolts plus 2, which is equal to 20 plus 2, which is equal to 22 mm. Again, this
Uh,
H is in suffix.
Bhargav, how do we know that the clearance is 2? Is it given or how do we like
It's not given, but from this particular table, we sort of have an estimate that for this particular bolt range from 16 to 24, it's 2. Now, I am going on and telling you that irrespective of what the diameter of bolt hole is given in the numerical, if you assume it to be 2, I'll be okay with it. Because the objective here is not to remember this table. The objective is to just understand the bolt hole, the hole diameter is slightly greater than the bolt diameter, and 2 is a reasonable number to start with. So you can assume it to be 2. Okay. So this sort of gives us the value of BH. Now moving on, we have to find out what is the net area. The failure path is only one failure path, which is 1, 2, 3, 4, 5, 6. That's a failure path. The net area in this case is equal to capital B minus n times of DH to E. Okay. So along this path, our width is 260, which is given in the question, and also 60 times 3 plus 40 times 2 is 260, minus n. Number of bolts is 1, 2, 3, 4. There are 4 bolts. So 4 into diameter of each bolt hole is 22, and the thickness is 10, is given in the question. Therefore, what is the value of An? Come on, a simple calculation. What is the value of An?
1720.
1720. What is a unit?
Area, square meter.
Yeah.
Millimeter.
What is it?
mm square?
Mm square, because depth is in mm, width is in mm, or the thickness is in mm, so it is mm square. So this is your answer. Simple, very straightforward. Any questions? Great. Now let us just change the arrangement of this bolting from chain bolting to staggered bolting. Please draw figure B. I've just numbered these endpoints of a path or the intermediate points of a path. This is 1, 2, 3, 4. It might start from here. So 5, 6, 7, 8. Oh, I've made a small mistake here. Moving 9. So, do you need more time? Can we proceed? Okay. So here as well, the diameter of bolt is 20 mm. The diameter of hole is db plus 2, which is 20 plus 2, which is equal to 22 mm. Now here, we cannot say with certainty as to which is the easiest failure path. So we'll have to do some calculations. Okay. So let us sort of look at various failure paths one by one. Okay. Now just pay attention to this. So the first possible failure path is 1, 2, 3, and 4. The second possible failure path is 5, 6, 7, 8. The third possible failure path is 10, 11, 12, 30. Okay. Now tell me, which do you think should we look at between 1, 2, and 3? See, we are trying to find out the minimum value of an. So we are trying to find out the path that has maximum bolts. And further, in the next step, we are going to find the path that has minimum staggers. Okay, so maximum bolts and minimum staggers. In this step, this is our step right now. So, which of the three paths do you think would occur?
Second.
Path number 2, right? Because there are 3 bolt holes. So naturally, there's the net area of this path is lesser as compared to these 3 paths. Okay, so this is how we eliminate our work. We can, of course, look at all the failure paths, which might be 20, 25, whatever. And just a number. I just mean to say that there might be a lot of failure paths, but we're not going to look at all of them because we are going to use logic to minimize our work as much as possible. Okay, so she has correctly pointed out that second or the path 5, 6, 7, 8, 9 is more probable as compared to 1, 2, 3, 4. But since we are doing it for the first time, let us sort of go by process. So first possible failure path is 1, 2, 3, 4. In this path, okay, this is just for your understanding. Do not write this in the examination or do not think that this is the way to write it. In this path, you have 3 bolt holes, and in this path, you have no staggering arrangement. Okay, this is just for your understanding. So an here is b minus n times of dh into t. B is 260. N is 3. N is 2 because there are 2 bolt holes into 10. Can someone quickly give me an answer?
Two 2160.
160 mm square. That's our first failure path. Now, let us look at the second failure path, which we are sort of sure that this is going to give us a smaller net area. The next path is 5, 6, 7, 8, 9. Along this path, we have 3 bolt holes and 0 staggered arrangements. So 6, 7, 8 are the bolt holes. In that case, we have 260 minus 3 times of 22 into 10. Can someone quickly give me a number?
19.
1940.
1940. Perfect. Okay, please, use the prefix, suffix, whatever. By now, you must be aware as to where to use the suffixes. Now, let us make things a little more interesting. So these were the linear failure paths, or these are the failure paths that are perpendicular to the tensile force. Now let us explore the other types of failure paths wherein we'll encounter these staggered arrangements. Would someone like to start with the path? Come on, be quick. We don't have much time.
1, 2, 6, 7, 8, 9.
1, 2, 6, 7, 8, 9. Okay. That seems like a path that could give us the minimum net area 1, 2, 6,
10,
7, 8,
7,
9.
6, 7, 8, 9.
What? 10,
10,
11, 6, 7,
11,
8,
6,
9.
7, 8, 9.
Okay, now we have another option 10, 11, 6, 7, 8, 9. So these two paths are going to give us the same value of net area because both the pitch distances are same. There's only one stagger that has the same pitch distance. So you can call this path as 1, 2, 6, 7, 8, 9, or you can call it as 10, 11, 6, 7, 8, 9. It's one and the same. But now, so along this path, we have 4 bolt holes and we have 1 staggered arrangement. Now our formula for AN is slightly different. So in this case, AN is P minus N times of TH plus summation of, I'll just write it, sum here, you give this sign. Summation of P square upon 4 times of G. And you multiply this entire term by T. So our B is 260. 60 minus number of bolt holes is 4. So 4 times 22 plus. There's only one staggered arrangement. Therefore, it is P square by 4G. P is 50. 50 into 50 divided by 4 times of the gauge distance is, so pitch is 50 and the gauge here is 60. 50, 60. So P square by 4 times of 60. And then we multiply this entire term by 10. Someone quickly give me an answer.
1824 mm square.
1824 mm square. If someone finds out this answer is not correct, please point that out. The entire point of this exercise is I want you to solve along with me. I don't want you to just copy the numbers that you see on screen. Yes, 1824 is also the answer that I am getting. Okay. Next possible failure path.
Uh, 2, 3, 7, 8.
It cannot start from 2, it can start from 1, 5, or 10.
1, 2, 3, 7, 8, 9.
1, 2, 3. It cannot go like this, so it can go diagonal or it can go down. It cannot go sideways.
Okay.
Come on, try another
1,
path.
2, 6, 3, 8, 9.
1, 2, 3.
6, 3, 6, 3, 8, 9.
Okay, 6, 3, 8, 9. Okay, this was a good example. So it cannot be 1, 2, 3, 6. It can be 1, 2, 6. Do you mean this?
Yeah.
So you might not expect this to occur because this is a shorter path for it to travel ahead of 6. So for the purpose of calculating, we might do this, but if 6 to 7, this is path number 1, 6 to 3, path number 2, 1 is easier than 2. Therefore, we can do it, but we'll not do it because we sort of know that that is not going to give us an answer. Come on, there is just so many possibilities. Just pick one.
1, 2, 6, 12, 8, 9.
1, 2, 6, 12, 8, 9. Yeah, that's possible. That's possible. Okay. So our next failure path is 1, 2, 6, 12, 8, 9. How many bolt holes along this path?
4.
4. And how many staggered arrangements? 3.
I'm just asking, but isn't this the same as the previous one which we were not doing? Because, like, isn't this the same as
Yes, you're correct.
okay.
It's the same one. From 6 to 7, 6 to 12, it will travel from 6 to 7. So any
So
other
with the
possible?
exam, do we have to like reason it out why we're not choosing
No.
a certain?
No. What matters is you get the right answer. If you do
Okay.
it in the first go, you get full marks.
Okay.
So you just use logic while selecting these paths.
Basically, we just get the correct answer and mentally we can calculate the rest.
Yes. So any other paths
Uh,
that you would want me to try?
okay.
So can we
Also,
try this?
I
1,
kind of have to
2,
leave for
6,
setting up
12,
encounters
13.
and
Sorry?
everyone will have to join soon as well.
Yeah,
I have
go
to
ahead.
kind of leave to set up the encounters and everyone will also have to leave in a
Yes,
bit.
let's finish this in a
Guys, please
couple of
join
minutes.
encounters today.
So 1, 2, 6, 12, 13 is the next possible path. Let us say 1, 2, 6, 12, and 13. And along this path, you have 3 bolt holes and you have 2 staggered arrangements. So your net area would be 260 minus 3 times 22 plus. So there are 2 staggered arrangements. In the first one, the pitch is 50, the gauge is 60. In the second one, the pitch is 50, the gauge is 60. So 50 into 50 divided by 4 into 60 plus 50 into 50 divided by 4 into 6. And then you just have to multiply this entire thing by thickness. Can someone quickly give me an answer to this? So the answer that I'm getting is 2148 mm.
Yeah, that's same.
Okay. So now just look at this. Just look at these numbers. 3 bolt, 2 staggers, 4 bolt, 1 stagger, 3 bolt, so on. So basically the failure path that had maximum bolts and minimum staggered arrangement gave us the right answer. So in exam, you basically have to look at a path that gives you maximum B and minimum S. Okay. Here we had 3B and 2S. Definitely that's not going to give us the right answer. Here 3B 0S, perhaps we'll have to see. But here, only along this path, we have 4 bolt holes and only 1 staggered arrangement. Therefore, we can say with a lot of confidence that this might be the failure path. And in all the other failure paths that have more staggers and same or lesser number of bolts, it's definitely not the right answer. Okay, so just another example. So another possibility, if you had say 45 instead of 50 here, so you already know that in between 1, 2, 6, 7, 8, 9 and 10, 11, 6, 7, 8, 9, which path will you choose?
1, 2, 6, 7, 8, 9.
Naturally 1, 2, 6, 7, 8, 9, because this is 45, this is 50, this distance is going to be lesser than this. So this pitch is 45, this pitch is 50. We have P square by 4G. Okay, so whatever has a lesser value of pitch, you'll choose that. So 1, 2, 6, 7, 8, 9 has lesser value of P, and therefore that would give you a lesser area. So use that sort of a logic to simplify things and reduce the number of attempts. If required, we'll solve one more problem on this. If this concept is clear, I think we'll stop here and we'll move on to the next concepts. Okay, so I believe that you have to rush through your encounter. So I'll stop here. That's all from my side for today. Please go through the presentation. Please go through the numericals that we've solved. And we'll continue tension members in the next lecture. You will not have a test because I want to finish tension members before we have a test. We won't have a test in the next lecture.